Okay, so we're approaching the new topic from direction of linear approximations. Okay, so that's calculus 1, and replacing a function with its tangent line. That's the approximation. That's the basic idea of differentiation. So the graph touches the tangent line touches the graph, and that's why it is considered a good approximation. You zoom in on the graph. If the function is differentiable, the two merge. Okay, so taking a broader view, we started with constant approximation, sort of downgraded it from linear approximation, and just to demonstrate that approximation is better, we have this picture, approximation of the square root of a function at or around x equal 4. This is x equal 4 somewhere. And as you can see, the approximation is better just by looking at it, but more important, I suppose, is that you can actually look at where the error is. This is the error of approximation. The difference, we approximate one function with another. So what is the quality of approximation? It is the difference between the two functions. So the function is the blue. That might be unknown, but if it is, then the difference between these two functions constitute a new function. And the size of that function is evaluated in some way, will give you the error. So the error is on the left is fairly large, but on the right, this is the error. Okay, so once again, the difference between the two functions, which we already have seen over here. So this is the difference between the two functions that we take. So this is the error between the function and its approximation. And at the very least, what we require that error to be is that it converges to 0 as x approaches a. It is very easy to accomplish, and that's what we see in the picture in the middle. The two graphs, as long as they intersect and both of the functions are continuous, we're going to have that property. Okay, and we also, the second requirement, I suppose, was that pick the simplest function possible, and so we picked the constant function, as you can see. But then we moved on to linear approximation. What does linear approximation give us that a constant approximation does not? And it gives you, that is still our error. This is still my error. But now it converges to 0. Still is converging to 0, but converges faster. It converges, even if we divide it by x minus a, the whole thing still goes towards 0. And that is the standard of better approximation. Okay, you can see it on the picture. You can see it also on the as the formula. So the best approximation among all linear functions. After all, constant function is also a linear function. So we just we on one hand we put allowed ourselves to have other functions than just a constant. But we also put a higher standard on it. We want this condition to be satisfied. So among all the linear functions that still pass through the origin, okay, through that point, okay, we picked the best one. Which one turns out to be the tangent line? So that's illustration here in the second row. Picking out of all lines, straight line passing through the point, we pick the one that has that satisfy this property in green. That's the best one. And based on that, we concluded, in calculus 1, then all we need to do to satisfy that property is to have the slope of that tangent line, to be equal to the derivative. In other words, and that exactly means that our line is simply the tangent line. Okay, so that's the conclusion from what we did. Okay, so that works out fine. Approximation, as we saw in this example, is better by far. The approximation, constant approximation, is right here. This is the constant approximation. The square root of 4.1. So what's the best approximation? It is function is 2, y equal 2, and so the answer is 2. Okay, but if we approximate it with a linear function, as we did next, the answer was this. 2.025, and it is better to the number that we saw. It is very close to the number that we saw on the calculator. It is possible that the calculator does it in fashion similar to this. Okay, so can we do better? The answer is yes. and the answer is to involve quadratic functions. So the picture suggests that it is possible to have, if you allow your approximation to curve, you can certainly make it hug the graph of the function better. Okay, so that is out of those bunch of parabolas that you see, you can pick one that approaches or approximate our function better than the straight line that we have over here. So that's a straight line, but some of these might be better. Okay, so what is the standard of better? And the answer is this limit. Okay, I didn't write it yet. The limit is, so okay, it is a linear approximation. So that formula is, it means simply that this is a quadratic approximation. And then turns out, then we put what is the standard of a best approximation. We have the error. So this is still the error right here. The difference between the two functions, our approximation and our function. This is the error. Once again, it is visible in the same place. Let me show you once again those errors. So this was the best constant approximation. Is this these are the errors? Okay, best linear approximation is very hard to see, but it is here. Okay, so these are the errors. A function that represents the error, and as you can see, it is 0 in the middle, and then it grows as you move away from the origin. Here it is impossible to see. I don't even see which one. Well, there's an arrow there. With this thing. Where is it? Okay, I don't know what it is. Okay, so that purple arrow actually points at our best approximation as a result. Okay, so the error is tiny, even though the previous one, the linear error, was small enough, but this one is even smaller. Okay, certainly we can see that we're doing better and better every time. Okay, but the standard is that the error not only going towards 0, but it's going towards 0 even faster than before at a different rate. So this was a rate that is faster than x minus a. This is 1x minus a squared. Okay, so that is the standard, equal to 0. And then it turns out that as it was suggested yesterday, the answer is what that quadratic function should be, and the answer is that number p, that is the only one missing, that number p, this one. We need to figure out what it is. The rest I already know. So it has to pass through the point. That's guaranteed here. It has the same slope. It's guaranteed here. The third one is the last term. That the only room that's left for us to vary, and that's the picture that you see here. Same point. Look at those parabolas. They pass through the same point, and they have the same slope at that point. Okay, so that is the standard that we took from the previous step when we picked the tangent line as the approximation. Now among these, there's still many of them rather than one with these properties, and we picked the one, and it turns out that what was suggested yesterday, that the answer lies in choosing, in making this function to share the derivative. Okay, so so the answer is that number p is in fact, it is not the derivative, but not the second derivative, but derivative divided by 2. We'll see where this by 2 comes from, but that is the answer. So the function, how to approximate the function with the using not only the value, the derivative, and the second derivative. That's how. Okay, let's confirm that if at all possible. Let's confirm that idea with the same example. So remember, our f of x is equal to square root of x. Okay, so the derivative is 1 over 2 square root of x. Okay, which is, as I recall, equal to 1/4 at x equal to 4. Okay, and we're moving to the next step. So we don't stop here. We're moving on to quadratic approximation. So this is constant. This is now gives me a linear approximation. We just looked at that. And now I'm moving on to the quadratic approximation that we see here. And we're going to need the second derivative. Okay, so f double prime. I'm going to differentiate this. How do we differentiate this?
Same way you did before.
Okay, so
you just bring out 1/2 and then
okay,
multiply that by 1/2 again, right? Would it be 1/4 x squared or x cubed?
no, you gotta use the power formula. So this is x 1/2 as a matter of fact. And that's how we got, and this is x 1/2 x negative 1/2. So that's how we differentiate by power formula. So the power goes down by 1. 1/2 minus 1 is negative 1/2. Okay, and that's the extra 1/2 there. So we use the same thing. So square root is not convenient for differentiation. It doesn't have a convenient formula, but the power formula is available, and we just convert every time to formula for whenever we see roots, we convert them to powers, and then we differentiate like this. Okay, so what do I get? 1/2 times negative 1/2 x to negative 3/2. Okay, so in other words, we have negative 1/4 and negative x 3/2, which is equal to what at x equal 4? Let's see, what is it equal? X equal 4. Negative 1/4 for negative 3/2, which is 2 to negative 3. Right? No, not negative, just 8. Why? Yeah, okay, so in other words, it is negative 32, negative 1 over 32, right? Okay, so that is our second derivative at that point, and along the value of the function, well, actually, f of so this one is equal to 2 at x equal 2. So these are the three numbers that get involved, 1, 2, 3, that will give us what? It gives us the coefficients of our quadratic polynomial. Quadratic polynomial has 3 coefficients, and all 3 will come from these numbers, except, as you can see, the formula right above, circled in purple. It is you don't take the value of the derivative, you take half of that. Okay, so in other words, it will be what is our formula? Then the quadratic polynomial will be where's the formula is right here. A value of the function. Okay, I'll try to fit it in right at the top. Value of the function, which is 2, okay, plus the derivative, which is 1/4 x minus 2 or 4, right? Plus p, which is derivative over 2, so it will be negative 1 over 64, right? X minus 4 squared. Okay? So that is a quadratic approximation. You can actually see what is the significance of the negative sign at the end. Negative 32, negative 60, negative 1 over 64. What's the significance of it?
Is that how much more your approximation is?
Yes, but still so you're subtracting, yes. So
that's the difference
between this and what?
in the original.
That's right. This is L of x. The linear approximation is the first two terms. Well, let me confirm. Right here, see, this is the one. This is our linear approximation that, once again, comes from calculus 1. And we have an extra term. We added an extra term, which happens to be negative. At least when it happens to be negative, what does it tell you about this approximation? Well, you have a linear function and then you subtract. What happens to the function? Well, I mean, you subtract and it becomes smaller, right? So it will lie below that straight line, right? So a straight line, this is a straight line like this, and then we subtracted some, and then so it will be lie here somewhere below it. Okay, but it's more specific, so it's not going to look like this because it's a quadratic polynomial. It doesn't do all this all up and down. But still, I want to ask you. So what the second derivative is negative. What does it tell you about the function? Negative second derivative. What's the meaning? What's the sign of the second derivative? The sign of the first derivative? What's the importance of the sign of the first derivative?
Whether it's increasing.
Increasing, decreasing. Okay, what about the second derivative?
Concave
Concave up, concave down. So because this is negative, it means that it's always negative. No matter what x is, this thing will be negative. So the graph is, so the function is concave, concave down. Concave down. It is exactly what we saw. These pictures are, in fact, that's where they came from. As you can see, I mean, it might be a bit hard to see, but that purple graph, so the blue graph is the original square root of x graph of the function. Okay, the purple one, you can almost see it. Let me try to this. Well, it's a little bit harsh. Even though to the left it is above and to the right it is below, or vice versa. To the right it is below, above, and here it is above. Nonetheless, it is clearly concave down. It's really no surprise. After all, it is a quadratic polynomial. And you remember, the coefficient of x tells you whether or not the parabola branches up or branches down. So this one branches down because the coefficient of x will be negative. Oh, I'm sorry, of x squared. So it will look like this. Concave down parabola. In other words, it has a tip, a maximum, and the branches are pointing down. So so you can certainly try to improve. Okay, let's see if we are. We already have evaluated this. L of 4 is that we have. I don't want to do it one more time. L of 4 is 2.025. 2.025, and we are subtracting an extra term over here, which is, let me evaluate it if it is at all possible, 1/64 times 4.1 minus 4. Remember that the original problem was to approximate the square root of 4.01. Okay, and that was our linear approximation. Now, the quadratic approximation subtracts an extra term. Does it make things better? Maybe. So it will be 0.1 divided by 64. Okay, let me try to do that. So what is it gonna? So it will be 0.1. Oh, that's right. Yeah. Thank you. That matters. You squared. Okay, so it will be 0.01 here. Where's my calculator? 0.01 divided by 64. So that's an extra term, very small term, but let's see if it brings us where it brings us. So then I will add 2.025, which gives me 248. Okay, 2484. 2484, 375, 37502. Okay, so this is the answer. Where's that thing? Oh, here it is. So this is the approximation. This is the approximation of square root of 4.01 quadratic approximation. So this is linear, and this is quadratic. Well, let's see what the calculator does. Does it do linear approximation or does it do quadratic approximation? So let's just take 4.01 and take a square root. 4.1 and square root. Where's my square root? Here it is. Okay. 48485. That's, can you see where the difference starts? After 8 and 4, the calculator has 5 and 6. That's what the calculator gives me. So as you can see, we have how many digits after the decimal? 1, 2, 3, 4, 5 decimals coincide. And we are closer, or rather, we are closer to the result calculator provides with than with the linear approximation. Okay, so maybe it uses a quadratic approximation, maybe it uses cubic approximation, maybe so there are some tricks that they also have. But as you can see, the calculators, the trouble with square root, as we talked about yesterday, is that you cannot compute it in any direct way. All we know about the square root, about this number, is when squared, it is supposed to produce. Is supposed to produce 4.01. That's all. Wait a minute. 4.1 or 4.441. It produces 4.1. Okay, so which means that these indirect methods that you go backwards from squaring to square root, you have to develop some methods that are indirect and therefore approximate. You can square a number directly by just multiplication, but taking a root is not. So then the trouble is then there are so many operations that can like that. So you have to develop methods. There are just too many functions to worry about. So you have to develop, for any kind of computer or calculator, you have to develop methods that approximate things. And that's one way to do it, is to approximate one point at a time by tangent line or quadratic function, and then kind of in a way, if you think about what it gives you altogether, if this is my graph, okay, and then I have a couple of points like this. This is not here, maybe here. So this is 1 and 2. So these are known. These are known. Okay, and the rest is unknown. So what do we do? But the derivatives are known. So what we do, if we are just doing linear approximation, we are building a new function, maybe like this: tangent line, tangent line, tangent line. Okay, so and then we try to build maybe a kind of glue it together, these tangent line into one curve, maybe like this, and it will be something that we can use for computation. So that is an approximation as we see it. Wherever the blue numbers, the blue curve is, we don't know, but now with that curve available, if we pick any number here or there, we can easily now find the value by direct computation. So if everything is linear, then the computation that we have to carry out are very direct. They are just addition and subtraction. We just did it. Notice what we did. We carried out this computation entirely by hand. The only thing that was non-trivial, but it's still, calculator still might do it, and that is differentiation. Otherwise, the algebraic operations were entirely like middle school. So square root doesn't come into play, and you can do it with well, it was I suppose it was ironic that I used the calculator to to do that, but we could have. We did not, but we could have. We could have done this. I guess that is the important point. We could have done this, or that can be done. Just you don't want to do it without a calculator. In reality, calculator does it, but it does these operations. It does these operations without need to approximate. That the difference between these operations and the square root is that, once again, square root needs approximation. These do not. So subtraction, what did we do? We did subtraction and multiplication for the most part. And these operations can be done because they can be done by hand. Also, calculator can do them by simple computer operations that do not require approximations. Okay, so let's see. Okay, so but we are not stopping here, and the idea is to develop this theory into something bigger, and that is approximations of any degree. Okay, so that's our goal. So this is a linear approximation, one point at a time. Quadratic approximation will look better, but still not a very, still, well, it will hug the curve much better, but you can tell it straight line from not straight line. So the quadratic, at least you can recognize it. Beyond that, they will become so close to the curve that you cannot tell them apart. So let's do one more example of quadratic approximations. I'll take the cosine x equals 0. Differentiation, all are very simple, and cosine x. Okay, so we differentiate. So f of x is equal. So give quadratic approximation. Of f of x equal to cosine x at x equals 0, or around x equals 0. Okay, so f of x is cosine x, so f of 0 is equal to 1. Okay, so remember the formula is still the same. My formula, this is, I guess I just should write it out. This is my main formula for the time being, is this. This one. Okay, so once value, first derivative, second derivative divided by 2. I probably should write it out before we move on. So quadratic approximation is f of a plus f prime of x, f prime of a, x minus a, plus f double prime of a over 2, x minus a squared. Okay?
Now, if we want to do a cubic approximation,
Yeah.
you just tack on 3 instead of 2?
Actually, it's 6.
6?
Yeah, you divide by 6. You can see where it comes from. Well, you will see where it comes from, but it comes from differentiation. So if you differentiate once, that 2 over here, that 2 is this. Okay, so when you differentiate once, try to differentiate this function, this function, q of x. You differentiate it with respect to x. What are you going to get? Well, let's do it. Q prime of x is equal to, let's differentiate. Well, it's a good exercise. What's the derivative of this? Term by term?
F prime of a.
No. Term by term. Derivative of the first term is 0. It's just a constant number, f prime of a. That the a is our number where the location we concentrate on. So it's just a number. It disappears. It disappears. And then, okay, now what about the second term? So 0 plus, what's the second term?
F prime of a.
F prime of a.
X minus a.
What?
It'd be times x minus a.
No, we're differentiating it.
Mm-hmm.
So x minus a is gone.
Right.
Okay, so that's the second term. Right?
Right.
Okay. And the last term? I understand the challenge here is that the formula is kind of complicated, and the function is here appears to be there, and you want to differentiate it. But just once again, remember this is a quadratic function. It is only x matters as a variable. We're differentiating with respect to x. So everything else, this is a constant, that is a constant, this is a constant. Okay, so what do we do with constant? We use the constant multiple rule. So the derivative is nothing. So what I have then is f prime, where is it? F prime, f double prime. Well, you tell me what the answer is. Well, f double prime of a over 2. What's the derivative of what's left? 2x minus a. What's the derivative? X minus a squared derivative is with respect to x. So these are the same. And now I need to differentiate the last term. 2x minus a. But by the chain rule, as a matter of fact. Right? So derivative of x minus a is 1. So that's why there is no extra term.
Now, do the 2's cancel out?
They do cancel out, so the final formula will be f prime of a plus f double prime of a x minus a. So as you can see, 2 cancels out. If we had a third term, then and we would also cancel 2 out. We would cancel 3 out. So if we had a third power, when you differentiate, the same thing happens, and 3 would be canceling out. But then you would have to differentiate one more time. So and that's how you end up with 6 rather than 3. Well, anyway, that will come up a bit later, but let's finish this computation. So this is what is the derivative. This is the derivative of my quadratic approximation. Okay, what is the second derivative of our quadratic approximation? F prime of a is yeah, derivative is 0, right. And so what we're left with, now we differentiate the second term, what do we get? That's right, that's it. Well, to be expected, we ended up with nothing but a number. That is a number, so the second derivative of the function is a number, which means the function is quadratic. We knew that. Okay, so it's not surprising. Also, as planned, we discovered that our function, quadratic approximation, shares the second derivative with our original function. Okay, so, well, that's good. So it shares the value, the first derivative, and the second derivative. Okay, so so it's all here, and that division by 2 comes in very handy because that ensures cancellation. So we will have to carry this out, plan all the way through, 1, 2, linear, quadratic, cubic, and to degree n, and in fact take a limit of that eventually. So that's the plan. But at this time, let's just carry out this plan for cosine around 0 and see how well it approximates things. Okay, so we have our function. Now we are doing it. The derivative f prime of x is equal to negative sine x. We plug in, always plug in. We're not dealing with the derivative of f prime, but the derivative of f prime at 0. So f prime of 0 then is equal to 0. Okay, f double prime of x is negative cosine x. f double prime of 0 then is equal to -1. So the best quadratic approximation, Qx, is, okay, so this is the formula on the right. Not this one, but at the top over here. So f prime of a, which is, it doesn't fit, but f prime f of a, which is 1, plus a derivative, which is 0. Well, just in case I write it here, even though it is 0 term, I just want to ensure that we match everything that we have in our formula over the quadratic approximation. And then the second derivative divided by 2, so it's -1 divided by 2, x minus 0 squared. Okay, so I just plugged in those 6 numbers into my formula. Okay, if I simplify, I have 1 minus x squared over 2. Okay, and by the way, I can see in the quadratic approximation, that's the advantage of this method, or of what we're doing, if we do it one at a time, we have all the previous approximations still visible. Okay, so in fact, what is the constant approximation? So this is quadratic. Quadratic approximation, where is the constant approximation? You can still see it in the formula.
The y is 1?
It is 1, yes. It is 1, right? Now, it's a bit trickier, but what about the linear? No. A linear approximation shares the point. It still has to pass through the point 1, 0, 1. So, what is it? Oh, the answer is 1. Okay, so after all, constant function is a linear function. It just happens because the middle term is missing. Over there, we ended up with 0. Over here, there is no change of slope. So as the slope was 0, with the constant approximation, it remains 0. Okay? So this is the illustration I have somewhere. No, just a minute. Here somewhere. Here it is. Okay, so the blue one curve is a cosine. Okay, the red one is the constant approximation. Okay, through this is our point of interest. Okay, where's the linear approximation? The answer is that red line is also the linear approximation, because look at it, it is tangent. Linear approximation is the tangent, and so we found it on the first step. First step gave us constant approximation, just happens to be also the linear approximation. Okay, and the quadratic approximation is that parabola. You can certainly once again see how well it approximates the curve in comparison to the straight line. Okay, so then what is the plan? Well, why we're not satisfied with that? You can see that the green one it does very well around here, right? Really well, but then look how awful it is outside. As we move away from the origin, the approximation fails miserably. And in fact, the parabola will go to infinity. That way, in the meantime, the cosine is simply going up and down from left to right. Okay, so that is what we want to do a better job. And if you think about, say, quadratic, or especially, well, quadratic now, cubic, and 4th degree, 5th degree approximation, they will look better. And for example, we might end up with something like this. That would be a 4th degree approximation, something like that. So once again, we'll look into those as well. Okay, so now we just want to try to have a general approach to it, and we have to look at polynomials first. So just polynomials, forget about approximations, we just speak of polynomials. And as you have noticed, we look at them slightly differently. I'm not sure if you have seen this before in pre-calculus. The polynomials, nth degree polynomial, is a sequence of these terms, say a naught plus a1x plus a2x squared an xn, an not equal to 0. Okay, so that's what an nth degree polynomial looks like. So you have n plus 1 numbers, you align them with the powers accordingly, powers of x, and then add them together, and that's how you have a polynomial, right? Sounds familiar? Okay, but what is not, what is x if not the distance to the origin, okay, of your location? So what if we interested not in x but rather in like location not at 0 but at point A? So we have a different kind of polynomial, which is the same polynomial, just a different form, and that is a polynomial. So once again, nth degree polynomial centered at x equal a. Okay, so say q of x. Now let's do p of x. P of x looks like this: a c naught plus c1 x minus a. This should look familiar already. So we have all the powers lined up in the same manner, but this time we are looking at not at powers of x, but rather powers of x minus a. So we are looking at how this is the what we have expressed our polynomials in terms of this. So a is our point of interest, and if the point x is here, then we're looking at x minus a. So the distance to that point. So as if a is our origin. Okay, so we are, because we cannot fully concentrate entirely on the on 0 at a time, or 0, that we want to be able to center at any point that we want. You already saw we did exactly that. That's these terms x minus a that appear and reappear are in fact just a special feature of polynomials that can be done every time. So can be rewritten. So, and any nth degree polynomial can be rewritten in this fashion for whatever point A you pick. The coefficients change, as you can see, but other than that, the look is very, very much the same. You remember that polynomials are the easiest functions to differentiate. All you need is a power function. So fortunately, it still works out. So let's differentiate it. Well, before we differentiate it, let's notice that P of A is equal to C naught. Okay? Just as over here, P of 0 is equal to A naught over here. But here now we have P of A is equal to C naught. So that's the value of the function at A is a particular number that we started with. The first number in our sequence. So that sequences are starting to appear. Once you move from a polynomial, linear, quadratic, cubic polynomial, once you move to polynomials of any degree, you realize that what you're dealing with is sequences. So, and that is already a sequence over here. So C naught, Cn is a sequence. It is not an infinite sequence yet, but it's already a sequence. Okay, so let's differentiate. P prime of x is okay. 0 plus we just did it. Very similar. This one is simpler except more terms. Derivative of C1 x minus a. What is it? C1. C1. Okay. What about the next one? This one. Yeah, 2c2 x minus a squared disappears. Okay, and the last one? not 3, but
in
n Cn x minus a
the n minus one.
n minus 1. Okay, so as you can see, what has happened is the derivative of nth degree polynomial centered at a is a degree n minus 1 polynomial centered at a. Right? It's still centered at a. And we realize that turns out that C1 is actually P prime of A is C1. So the first term in our polynomial is in fact the derivative at that point A. Okay, let's differentiate a couple of more times. Double prime of x is equal to what? So 0 is gone, C1 also gone. 2C2 x minus a gives me what? X minus a is gone. Once again, that minus a really doesn't make a lot of difference because the chain rule applies and derivative is 1. So it will be simply 2C2. And the last one is, so you add all of these terms, and the last one will be, look at what happens. They start to accumulate. The derivatives, the coefficients start to accumulate after every differentiation. So I'm going to have n minus 1 Cn x minus a n minus 2. Okay? So that's why we end up with more and more terms. The more differentiations we have to deal with, more terms are involved, and there's every multiplication we will create a new bigger coefficient. Okay, but other than that, we'll have to do that as well shortly. But at this point, we just say, well, this is how. Well, let me write this. I forgot to do this. The double derivative of a. The double derivative of p at a is equal to 2c2. And then we continue on doing this with the differentiate. How many times do we differentiate nth degree polynomial until we stop? Okay, imagine that. Let's keep track of the last term. If I differentiate it once, the degree goes by 1. So if I differentiate n times, so this is 1, this is 2. So what's in the end after n differentiations? Nth derivative? n minus 1, what's the next one? You differentiate, when you differentiate n minus 2 over there, what happens? You'll have n minus 2, right? Then you keep going. And then when you have a third degree polynomial left, you have 3 after differentiation. Second degree polynomial, you have 2, and that's what you end up with. That's the nth derivative of the nth degree polynomial is this. It's a number. It's a number as expected. And remember what this is called? What?
Is this a Taylor polynomial?
It's going to be, yes, eventually. Right now we're just talking about polynomials. Taylor polynomials are functions that approximate functions. Right now we're just looking at a polynomial that does not serve any particular purpose. Anybody knows what this is called?
Factorial.
It's factorial, right? The factorial. Okay. All right, so we'll just continue.